We continue now with section 30.2. This is the general resistor, inductor, and voltage circuit. You notice we don't have a capacitor in here yet. We're working up to that. So we're going to imagine that we have a circuit. And the circuit is going to have a resistor, an inductor. This is going to be a resistor. This is going to be an inductor L. We come around here. We'll have a switch that we can turn on and turn off. Then it will have a voltage. Let's represent that by a battery. So here's our voltage V. And what we want to do is, first of all, use Kirchhoff's laws to say, if we throw this switch, certainly there's nothing happening here right now because the battery is not connected, so there's no current flowing. But if we throw this switch, closing this switch, then by Kirchhoff's laws, the sum of the voltages around here will be zero. And what is that? It would say that the voltage is plus the voltage across a resistor. Well, that opposes it. So that's going to be minus I times R. Remember, the voltage across a resistor is R times I, but it's going to be in opposition because they're going to oppose the battery, minus the voltage that's across an inductor. Well, we've just learned from our last section, 3.1, that the voltage across an inductor is L di dt. So now we can write that as L di dt. And the sum of those must be zero. Well, we can bring these to the other side of the equation. They become both positive, and we see that we can rewrite that equation as L di dt plus R times I is equal to the voltage. Now, first of all, we need to see what type of equation this is. It's a differential equation because we have a differential here. And if you do not know calculus, or if calculus is not required, then you simply will use the result of the work that we do here in deriving our answer and learn that answer and understand it. So we're going to learn how the current responds. Well, you can see that just intuitively, the current is going to push around through here. Electrons are going to try to go this way, so the current is going to flow actually this way. Remember, this is the positive end of a battery. This is the negative end. So although the electrons are going to flow this way, the positive charge would, quote, flow this way, and this would be the direction of I. Well, I is not going to want to change much because of this inductor. And then, of course, this dissipates some of the energy from that. So how do we describe this? Well, here we have a general rule that all linear second-order differential equations in first order, in fact in any order, have a solution that's of the form, here I'm going to write it in the form of I, this would be constant A times e to the alpha times t. In other words, you can always use an exponential to solve a linear differential equation. If it is inhomogeneous and has a constant on this side, we must add another constant to that. And then we have to say, for what constants, A, B, and alpha, does this represent a solution to this differential equation? Okay? That's what we're going to do now. It is a first-order, homogeneous, linear differential equation, and you can see here, as in the notes, we're going to solve it using this current, and we're going to get this result. But let's derive that and see how that arises. We're going to take, first of all, the derivative of this, and when we do, we get L times, well, what is the derivative of this? The derivative of an exponential just brings down a factor of alpha. So this is A alpha e to the alpha t, and the derivative of the constant is 0, so we don't have it, plus R times this whole thing, the current. That would be R times A e to the alpha t, plus R times B, and this whole thing must equal to V, which is the voltage. Now we can collect terms here, and so what we will we we will factor out the AE to the alpha t here, AE to the alpha t. And in front of this AE to the alpha t, we'll have L times alpha plus R. And that does give us the correct first term. It gives us the correct second term. And now we're going to take this term, this constant term, over here with this constant term, and have V minus R times B. Well, this is a paradox we've seen before. Here we have a function of time, so this side of the equation changes with time, according to either a constant exponential or diminishing or increasing or an oscillating if it's complex. This side has no time on it. How is it possible to have a function of time equal to a constant? Well, we can't unless this coefficient is 0 and this is 0. Then the fact that this is a function of time will not bother us. Well, the A can't be 0 and this can't be 0, so that means that we have the result L alpha plus R is equal to 0, and therefore alpha is equal to minus, there's a minus R, divided by L. So that's our first result, and it tells us what alpha has to be. Our second result tells us that V minus RB has to equal to 0. Well, now if we solve that for the constant B, then we see that this comes to the other side of the equation, and B is equal to V divided by R. So that determines the constant B. There is no restriction on the constant A, and that depends upon what is called the initial conditions. So what is our result? Our result is our solution, the current I used a capital I here also, is going to be equal to AE to the alpha t, that's A, E, and what's alpha? To the minus R over L times T plus B, and B is V over R. So this is our solution. That's our general solution, as it's called, because it solves all of this, any of the differential equations that we have here. Here's our differential equation. There's the equation. Here's the general solution. Now, that's not a specific solution for this exact problem. It's a general solution that would work no matter how we open or close the circuit or how much current is flowing when we do different things. So how do we take this and make it more specific? Let me get this lined up properly. So although this is the general solution, we now have to say what is our specific solution for this exact problem. And you always have that. When you have a differential equation, you can find a solution that's going to satisfy the general equation, but maybe not that exact problem. Well, what would satisfy this problem? Well, you know something very specific. You know that at time t is equal to 0, t is equal to 0, we're going to shut the switch. We're going to connect it. Connect the battery. This is what we're going to do. Therefore, at time t is equal to 0, we know that no current is flowing at that instant. So if we put in 0 here, then we get I is equal to A, e to the 0, which is 1, plus V over R. Now, e to the 0 is 1, so what we get is this must be 0. Therefore, we have A plus V over R is equal to 0. Therefore, it follows that A must be equal to minus V over R. So now we can go back and plug that in, and we get the current. And this becomes the specific solution. I is equal to minus V over R, e to the minus R over L, t, plus V over R. Now I can factor this V over R out and get V over R times 1 minus e to the minus R over L t. And this is the current I. This is what we call the specific solution. This is our current as a function of time. And you can see that when t is equal to 0, sure enough, this becomes 1. 1 minus 1 is 0, and so our current does start out correctly. And that's the condition that we had to satisfy. Whereas this is called the general solution. This is called the specific solution. And of course we could substitute any of the numbers in here. I want to point out the fact that this is a time constant here. Remember, all exponential functions must have dimensionless arguments. So this can be rewritten as, I'm going to use another piece of paper here. Here we have the form e to the minus r over lt. That can be rewritten as e to the minus t over L over R. And this L over R can be thought of as a time constant because this is seconds, so this must be seconds. So this is equal to e to the minus t over tau. That's what I use here. And tau is equal to L over R, and it's the time constant of the circuit. Tau is time constant. And this time constant is equal to L divided by R. And that's something that you need to remember. Because in the amount of time L divided by R, whatever that ratio is, like maybe it's 4, what happens in a time of 4 seconds, if L over R is equal to 4, for example, that would be 4 seconds, it would mean that e to the minus t over 4 at a time of 4 seconds, over 4 seconds, becomes e to the minus 1, where it drops to what we call 1 over e of the original in a time tau is equal to L over R. So this time constant tells us how rapidly this is changing, and it's going to drop to 1 over 2.718 and so forth in that amount of time. So you could expect on the test to have to know what the time constant is, how to plug it into your specific solution, and what the general solution is. Finally, finishing up section 30.2, we have an equation here for how much energy is stored in a magnetic field. Later on, this becomes very important. Energy in the magnetic field. That energy U is given by 1/2 of L times I squared. It turns out that energy is usually goes as the square of an amplitude or something like that. And in that last equation, you'll notice that the current was proportional to an amplitude A. Therefore, apart from this constant, we can say whatever the current is, its square gives us the energy. So that's what we have right here. Later on, we'll see that the energy stored in a magnetic field goes as B squared, and an electric field goes as E squared. And so you need to know how much energy you have stored there. Twice the current is flowing, you'll have twice the energy stored in that field. That finishes up section 30.2. And of course, if you put in 3 henries here, and you had a current of 2 amps, that'd be 2 squared, 2 times 2 is 4, 3 times 4 is 12, and 1/2 of that would be 6, and that would be 6 joules. And that's the way you would work a problem associated with that energy density.